quite high up. There's...
Sorry, that's me forgetting.
There we go. Yeah, so I can't quite remember quite how high up this is, but to be honest, it's just a pretty picture to entice you all in. So what am I going to talk about? So I'm going to first introduce simulation models in general, and I'm going to talk about what a simulation model is and some of the most important aspects with regards to calibration. And then I'm going to talk through calibration. So what calibration is, I'm going to talk about a lack of identifiability, give you a Gaussian process primer. How many people here know what Gaussian processes are and use them semi-regularly? Okay, this is good. So I'll give you a bit of a primer on this topic, and then I'll keep going with the Bayesian calibration setup. I'll give you a quick example, and then the final 5, 6, and 3 at the end are all quite short slides. So let's rattle on. Simulation models. So these 4 are 4 examples of simulation models. These are actually all ones that my supervisor, Serge, has worked quite closely with in the last few years. The weather and climate, he works quite closely with the Met Office. There's nuclear fusion models, which are with the UK Atomic Energy Agency, or UK AEA, which is really hard to say. And earthquakes and tsunamis, which he spent many years working on. There are, of course, other examples, but these are perhaps some of the most computationally intense examples, especially weather and climate at the top there. So what's the difference between weather and climate models? So weather models tend to have quite a fine resolution, and that is in spatially. They also have quite a short time step integration. So when they're iterating forwards in time to create the times that they're iterating forwards through tend to be gaps of about 4, 5, 10 minutes or so. They also tend to be, or can be, regional models, so they'll maybe focus on just the UK or on Europe or on the whole world, for example, which is different. And they tend to have a look ahead of up to 14 days in general, but after that, they start to become a little bit useless. Climate models, on the other hand, are quite different. They are very coarse in resolution and have a much longer time step integration. I'm not actually quite sure on what that figure is, but again, that will vary hugely depending on the model anyway. These almost always have global coverage, and the forecast period tends to be at least 100 years. And 100 years, I suppose, would be equivalent to thinking of things like anthropogenic climate change. It's also possible you could be forecasting thousands, tens of thousands, potentially even millions of years. The reason climate models have a much coarser resolution is to deal with this extended period of forecast that they're trying to simulate over. So weather and climate models, and most models, tend to have a grid. Obviously, weather and climate tend to have a nice grid that looks a bit like this. This design hasn't really changed much since the inception in the 50s and 60s. And we're starting to come to a point where this is becoming a problem. So you've got your longitudinal lines and your latitudinal lines. And as your resolution increases, because you've got more compute power, the gaps between your points starts to decrease. And as they get really close together, you end up with problems with numerical integration and whatever other processes you're doing when you're running these simulations. The next generation of designs for these kind of lattices aren't really lattices, they're called cubed spheres. And they're going to bring about a whole new host of problems. But for now, this is what the state of the art is, and it's not really changed for quite a long time, which is fine for now. But this is quite easy to split up. So you can think of this as, if you sort of unravel it, you kind of get like a nice square, except that we're also dealing with altitude. So we don't end up with a square, we end up with a cube. In this case, it looks like this colorless Rubik's Cube, I suppose. But obviously on a much bigger scale. Imagine just scaling it up. I couldn't find a nice picture online, so that'll have to do. Okay, so like an example. So the Met Office uses this system called MOGREPS for their operational forecasts. And to give you an idea of the scale of the data and the problem that they're dealing with, their grid has this dimension, so that's 1,280 columns going around the globe. There's then 960 layers going from the South Pole to the North Pole, and then there's 70 layers going out in altitude. This particular model has a time integration of 5 minutes, so it'll forecast 5 minutes, and then it'll sort of like reset itself and then do another 5 minutes, and it will create a 7-day forecast. Let's say you wanted to output one variable, temperature, on that grid every 5-minute integration for the whole 7-day forecast. That would require 347 gigabytes of data at float 16, which is not even a very accurate number, float 16. It's good enough for creating pretty plots, but it's not necessarily good enough to start a new simulation with this data. So that's enormous. And then you've got to remember that that is per variable, and that is per one simulation run, and this has an ensemble of 44 runs.
So to start a new simulation to be like losing some precision due to like storage. So what do you mean by starting?
So restart could be, so it'll do the 5-minute integration time forwards, and then it's sort of like, it's like, okay, that'll do. We've run those physics simulations for now. Now we'll start again. So you can save everything if you want to, but it will use a lot of data. So what you tend to do really is you'd only save an output for a certain location, or you'd only output the variables that you're interested in. So when you're launching a new simulation, you say, right, I want to start from now, you have to load all of this in. So you do need the vast amounts of data from that initial start point. I think they call them start dumps, because it is literally like a dump of massive amounts of information. So yeah, lots of data. And there's some examples of some outputs that you might be interested in. This is a minute collection of variables that you might be interested in. There's so many more. You could be interested in the chemical makeup of the atmosphere and how they might transport around the globe. Often these kind of models are coupled to ocean simulation models as well. So they've got their own model parameters and variables that I don't know about because I don't deal with those. But the scale of the problem can be gigantic. And that's just the simulations.
Just when you mentioned they reflect each other, and they're not independent. So in actually, you need extra data to sort of link the variances. Doesn't even be.
So it's just the state. So these models are not simulating, they're not stochastic in any way. They're completely deterministic. So they don't care for correlations. All they do is they say, this is the value at this point in time. It might consider the interactions of the points nearby, depends on how that process has been set up, but they're not necessarily considering correlations and things like that. There's nothing stochastic involved. Does that make sense? Yeah. So then there's your observations from the real world, and these can come from various different points as well. Obviously, this is more storage requirements, compute requirements. So weather stations are fixed in space. They don't usually look like that. They tend to be white boxes on the top of hills, but I think that one looks a bit like the Blackpool Tower. Satellites, they move. That can be difficult. Weather balloons move, but in a different way. And then, of course, ships and aircraft. And they all produce they collect different data for different variables of different quality, and you need a way to handle all of this. Is that all okay? I'm moving on. Cool. Okay. So all of these models, be it weather model, nuclear fusion model, whatever, they all have parameters. They need some sort of parameter that you have to choose, and it might describe the way a flow happens, a rate of a flow. It could be how certain processes interact. It could be anything of that kind of ilk. They all have to be chosen. And the question is, how do you choose them? So I'm sure a lot of us in here are familiar with perhaps how a machine learning engineer might approach this. They'll probably start off say, oh, it's easy. It's a numerical optimization problem. You pick a theta that just so happens to minimize some sort of loss. You know, you've got observations, you've got simulation output, just pick the best theta. Problem solved. The physicists, we go, no, that's not right. We know what these thetas are. They have physical meanings. So we can go out and we can do experiments and we can test for them and see what are these values. At which point, problem solved. So neither of these approaches work well enough for what we want. So the machine learning engineers found a solution that will produce fantastic predictions. Their models will look good, but the physicist is unhappy because that value might not be physically possible. It just works. The physicist will not be happy with the machine learning engineer because the value doesn't make sense, but their predictions aren't as good. So what do? You can got two different values of theta. You can pick one in the middle and upset everyone. You can pick the machine learning engineer approach and upset a physicist. No one's happy. So we need something better. And why doesn't this work? And these approaches don't work because there's too much uncertainty involved. There's uncertainty from the model. The model is potentially inadequate, which is a particularly harsh phrase, I think. But your model, your simulation model could be missing some parameterization. It could be missing some sort of physical phenomena that's just not there. Not because you can't include it because you don't know it exists, but because maybe it's a computational constraint. Maybe including that would just be too difficult, too time consuming. There's residual variability. So this is perhaps the difference between running simulations at different values of theta. So you can run it for theta 1 and theta 2, but you don't necessarily know what's happening in the middle, theta 1.5. It's not stochastic because if you run it, you know exactly what the answer is. But the way that we're going to treat this is as if this was a stochastic problem. Observation uncertainty, that one's quite obvious. You make measurements out in the wild and they're slightly noisy. Parametric variability comes from the simulation model will be made up of submodels, and each one of those submodels will have a certain parametric form. However it's been written, designed, whatever, that might be restrictive. It might not be quite flexible enough for what is actually happening out in the atmosphere, and that can introduce slightly more variability than you would perhaps like as well. And then there's the code uncertainty. This one's slightly dubious, so I'm actually going to skip over that one. Okay, so let's introduce some pretty letters. So we've got X, which we're going to define our locations with. This actually, we're also going to chuck in time in there. So it's basically pointing in X, Y, Z space and time. Observations, I'm going to denote by Z, and I'm going to make it explicitly clear that these have space and time by denoting it X of Z. We've also got the true process, and that is basically just the atmosphere. So we'll move on to we'll split that up in a second, how we're going to model that. But we're basically saying our observations are equal to the true state of the atmosphere plus some observation noise. That's quite straightforward. Next, we need to split up this true process. So we're going to say that the true process is equal to our simulator, eta. I'll describe those letters in a minute. And plus the model discrepancy. I'll define that as well. So eta, which has two inputs, are not actually two inputs. So we've already said that our simulators are defined on a fixed grid, and we can't really change that fixed grid. But we're going to have to pretend for now that, let's say, if you made an observation at this point and your grid points are sort of nearby, you could say, well, the simulator is going to be roughly this value in the middle of these grid points. The theta is our calibration parameter, and that is one of the most important things that we're targeting here. So that is what we want to know. We want to learn theta. We want to know what its mean value is, and preferably its uncertainty, its distribution. The other important thing here is the model discrepancy. And this is the difference between what the simulator thinks and what's actually happening out in the atmosphere. And this we have to learn. We can make assumptions about it. We actually learn a little bit about it from academics, from practitioners, but it's really hard to model. And we'll come on to that a bit more in a bit. Yeah, so the model discrepancy, that delta, represents all of the uncertainties that I listed, or most of the uncertainties that I listed just a minute ago. We sort of lump them all together because it can be really difficult to separate them all apart. But this whole equation here was first described by Mark Kennedy and Anthony O'Hagan in the paper from which I stole the title of this presentation. So, is all of that clear enough for now? I like the nods. Okay, we have a problem. Lack of identifiability. So we're going to jump back to this equation where we've split up the true process and said that it's just the same as our simulator output and some little bit of missing parameterization, this model discrepancy. Let's rewrite this. We've just reordered it. It's all we've done here. But it now takes a slightly different interpretation. So for any theta, so for any model parameter that we can pick whatever we like. We're saying that there is a model discrepancy such that this all agrees. So it doesn't matter what value of theta we choose. We can kind of describe some sort of discrepancy process that will fix our bad choice of theta. And this is true even if we know exactly what the true process is, which obviously we don't because we built a simulator for it. So this is bad. If you're a practitioner and you've just been told you can use whatever theta value you want, well, now how do you pick it? Well, obviously you've still got to learn the model discrepancy, and that's hard, and you kind of want to keep that as close to 0 as possible. Okay, sure. What does this actually mean? So we're not just learning about theta. What we're learning is a joint posterior, when we get to the Bayesian part, over both theta and the model discrepancy. We're learning the two together, and you can't separate the two. And what this actually means is that you end up with a manifold of the two. And it's then up to you how you pick the theta based on the model discrepancy. Even with infinite data, you can't learn theta exactly. Right, so what do we do? How do we get around this? So we need some sort of informative prior, and we need informative priors over both theta, our model parameters, and the model discrepancy. And this all comes from, well, the physicists and the model practitioners. So you go out to the physicists, they know what that theta will mean. It has some sort of physical meaning. They can give you a good idea of what that value should look like, how that should be distributed, things like that. And you do the same for the model discrepancy. You go to the people who use the model every day, who know how well it performs, how poorly it performs, and how to construct some sort of prior belief about your model discrepancy. Yes.
It's kind of not clear to me how that's done. Like, let's say you have some statistical model of
Yep.
the temperature of the fluid after a certain amount of time.
Yep.
And then the physicist says, well, we know theta is Navier-Stokes.
Yep.
How do you like encode the difference between like your probabilistic model and Navier-Stokes?
So Navier-Stokes, in this case, would be your weather or climate model, for example.
Sure, okay.
So that is, it's basically just an output. You're not necessarily, you're running the model and then taking outputs at every time step, or maybe at the end, you're just considered about, or only interested in the final iteration, potentially. So all you're interested in is like the field dump at the end, is the best way of dealing with it. And then you use that field dump information at the end to then you do the calibration on that. Is that okay?
Yeah, I think I'll learn more.
Yeah, so getting priors for these things is a lot easier said than done. A model practitioner will know how poorly their model performs, but trying to get them to describe numeric getting them to give you quantitative numbers is really difficult. And also you kind of need some sort of understanding of the structure of that error, which is also extremely difficult. This is not an easy problem before you've even started. And all of this, so this whole idea of the model discrepancy and the theta being coupled together in this way was presented in this fantastic paper. This paper also presents the idea that model discrepancy is essential. You could potentially do this calibration without the model discrepancy term, but your parameter estimates for your simulation model would be biased, and you would massively underestimate your uncertainty estimates. So that's bad, and you don't want to do that. Okay. So this is where I'm going to try and whiz through Gaussian processes as quickly as I can, which is also not easy. So what we're going to do, we want to model eta, our simulator, and the model discrepancy as Gaussian processes. And we're doing this for a couple of reasons. One of them is because the simulator outputs on a lattice grid, and our observations are not on a lattice grid. And the Gaussian process will provide a nice way of interpolating between the two in a nice structured way. And it also provides good uncertainty estimates, provided that everything is Gaussian, but that's the least of our problems. Okay, so the fantastic website for machine learning stuff, d2l.ai, catchy name, introduces Gaussian processes as a Gaussian process represents a distribution over functions by specifying a multivariate normal distribution over all possible function values, which is a lot of words and a bit of a mouthful. But if we work it backwards, it makes a bit more sense. It provides at all points in space, so if you imagine a line of x, at any single point that you fix x, we're going to define a Gaussian distribution. So you can have 3 points, and you're saying, I know at that point it's Gaussian, centered there, at that point it's Gaussian, centered there, and so on. It does look kind of ugly. So this particular Gaussian process, f of x, I have defined to be 0 everywhere, which sounds odd. Okay, so I've given you a random distribution over functions and then said, okay, on average, I'm going to give you 0. The k describes the covariance term, and that is how 2 points in space are related to each other. We get to choose that covariance kernel, that function. There are certain rules it has to follow and things that's not particularly important for this talk. What is important is that actually dealing with Gaussian processes in this form is a little bit difficult, especially when you're trying to implement them into computers. So what we're actually going to do is change the definition, and we're just going to work with a multivariate normal form because it's a much easier. So we end up looking like this, which is very similar. We've got a normal distribution centered at 0. X is now, oh, I've got rid of that. Oh, well, so X should have been just any kind of space. It's easiest if you just think that it's the reals for now for this example. K is now a matrix over a vector of points. And for any 2 points in the space that you're considering, you define that matrix such as that particular pairwise comparison becomes the kernel evaluated at those 2 points. Let's put a pretty graph up. So hopefully that makes it a bit easier to understand. So if you squint a bit and look at 0, so sorry, all of these lines are samples from a Gaussian process, specifically the one we've just seen. It has a 0 mean. And if you squint, you can kind of average them all vertically, and the average sort of passes through 0. The amount of wiggle is defined by our covariance kernel. And these are all different samples from that distribution. If you squint even more, you can kind of see that a lot of the data appears between -2 and +2. And that kind of makes sense as well. If we were doing a standard normal sample, we would expect it to be somewhere between -2 and 2. And that's what's happening here, but over a function, a line through some sort of space. Okay, so that's really pretty and colorful. What can we do with it? So the website goes on, it's possible to easily manipulate Gaussian distributions to find the distribution of one function value based on the values of any set of other values. So that's also a mess. But suppose we have 3 observations, Z1, Z2, and Z3. These are slightly noisy in this case, but we know that the function has passed through these particular points, or roughly with slightly noisy. We want to condition on those observations. We're going to vectorize it, just put it in a line. And then suppose we now want to make a prediction over a new set of points. So we know where we've gone through, we've made some observations, and now we want to make a prediction over some other points. This is about to get ugly, I'm sorry. So this is the distribution once we've conditioned on those points. The blue bit is just the mean. The green bit is just the covariance structure. The most important bit is that yellowy orangey sigma that keeps appearing. That's the only bit that's hard to compute. That is a matrix inversion, and that is of order n cubed when you're trying to perform that inversion. And that is the primary reason why Gaussian processes are expensive and difficult to use. There are ways around it. There are many different approximations you can use, but for this nice example, we're just going to assume that you can do this, and then it's not too difficult. Okay, equations gone. So I told you we've made 3 observations. So there they are. That's those black dots in the middle. The blue line is the same as the mean process that I just showed you. That was that blue equation from just the slide before. And around it, we've now got some uncertainty estimates. Great. Where do they come from? So that comes from the green equation on the previous page. And all we've done there is taken the diagonal of that matrix. And from that, you can get your variance at any point. The covariance is in the off diagonal elements. But if you want the variance at any point, you get that diagonal. And that's how you construct that plot in the middle. The right-hand side are samples from a Gaussian process from the conditioned Gaussian process in the middle. It is when you're working with Gaussian processes, it's always a good idea to work on both, or to when you're doing this, to sample from your conditioned distribution. And it's because once you've conditioned and plotted this plot in the middle, it can be quite difficult to see some of the structure that might be present in your samples. And in this particular case, you can kind of see in some places, especially of it here, where this line is dipping right down. It's not perhaps obvious that that might happen in this example. And it's a good idea to plot some samples and check to make sure you understand the structure of what's going on. Okay, last little bit. I brushed over the kernel functions. Here's 4 examples. They're all done pairwise. So on the left-hand side of each of these pairs is the actual kernel function evaluated at one of those variables is stuck at 2. The other one is left to vary. And on the right-hand side, we've got Gaussian process samples using that covariance kernel. So the first one is just white noise. There's only one sample, actually. Below that, at the bottom left, you've then got a periodic kernel. The one on the top right is the squared exponential kernel, which is actually what this is using. So you get these nice, smooth, infinitely differentiable curves. And the one at the bottom is a Matern 5/2, which is becoming very popular in the literature. It's twice differentiable. It's slightly more forgiving when you're using real-world data, but also has some nice properties as well. But these covariance kernels are not the main interest here. Okay, so why are we using GPs? They're flexible, they're non-parametric, and the uncertainty estimates are cheap once you've calculated that matrix inversion, which you're almost certainly doing because you need it to calculate the mean. So once you've calculated the mean, you might as well just calculate your uncertainty as well. Is that all okay? Lovely stuff. Right, we'll be going half an hour. Let's do some Bayesian calibration. Okay, so this is the model that we saw earlier. Observations are equal to the simulation output plus the model discrepancy plus some observation noise. I've changed the letter slightly. So instead of saying xi, I've now put xf. And the reason I've done that is xf is standing for the locations in space and time for where the field observations have occurred. And that is different from the next equation below, where xc is the points in space and time where the simulation has produced data. So I'm differentiating now between those two. So z is, are measured at points xf, and the simulation is measured at outputted at points xc. There's also another difference here in that t at the bottom is like theta, except that it's not quite the same. So t is where we have run the simulation model. They are specific values. We know them beforehand. They're not random. So you might say, I want to run this value of t equals 1. It might well be that theta is equal to 1. We don't know. But we know that we've run the simulation at this value of tc in this case. Yes, so we want to model eta, and so the simulation output and the model discrepancy both as Gaussian processes, except that we're not, because we're going to use the multivariate normal because it's easier to work with. Okay, some more equations coming, I'm sorry. Multivariate normals. In this particular case, I'm just going to define them as 0 everywhere. Whether that is sensible or not, and whether that's suitable for your application will vary. In this case, it's just a choice I've made, but perhaps not a good one. We also need to define the structure for these covariance matrices, sigma eta and sigma delta. And in this case, as we've seen, these are matrices, so each pointwise element of this matrix is given by a specific covariance function. These can be different for both the sigma eta and the sigma delta. Doesn't matter what they are. In this case, I can't actually remember what they are. But they'll almost certainly all come with some sort of hyperparameters, which I'm wrapping up in this variable phi. And to be honest, this isn't particularly important, but needless to say, these hyperparameters need to be estimated. And I'm just going to chuck a load of them into this variable phi, and we can kind of forget about them a bit, to be honest, for now. Okay. So the priors have been chosen by the user. Suppose we've done that. We now need to build some sort of statistical model. We need to build the likelihood. So this might answer your question now, Max. So this is how we're going to build up some sort of model. We're going to combine all of our observations and simulation output, and we're going to put it in one long vector. So we're going to start with our observations. That's our Z at the top. These tend to be significantly smaller in quantity than our simulation outputs, Y. And we're just going to lump all of that and call it D for data. And then on the other side, I don't actually think I use this variable in these slides, but implementation-wise, it's useful to build up this kind of design matrix, if you like, in this way, where the top few rows are then going to be the location points of the field data and theta. Remember, we don't know theta. That's what we need to learn. And then at the bottom, we're then putting the location points of the computer simulation outputs and the values at which we ran those simulations for the parameters that we're interested in. We're going to say that this is normally distributed. Again, whether that is sensible or not depends. We kind of transform it and hope that it is. But again, we're going to say that this is centered at 0 and with this covariance structure, where that's the covariance structure at the bottom. So this sigma D is equal to, so we're saying that all of our data, all of our simulation outputs and our observations follow the same structure as our simulation structure in terms of covariance and how those points relate in space. We're also going to add a little bit extra covariance structure to the observation point Z. And that's only on Z because it's accounting for the difference between the simulation and between the observations. Remember that model from before where we had the observations and then we had that's equal to the simulation output plus the model discrepancy and a bit of noise. The final matrix at the end is then just the observation noise, and that final term is very close to zero because it's basically a floating point error. You could probably get away with not including it. Okay. And there's a nice approximation for our posterior. So that's the model. We can run MCMC on this. And I hope what we get out fits nicely. Does all of that make sense? Some sense. I appreciate this is quite a lot. Those equations, to be fair, don't matter too much. The primary purpose of the talk is to get around the idea of the model parameters and the discrepancy term going hand in hand with each other. Yes.
So the Y is the simulation output.
Yes.
And they're using deterministic simulation.
Yes.
So why are we specifying a probability distribution?
So where was that? We've added a little bit of things at the end. So the way we have to construct this is we're building the emulator as well. So we know that the two don't align perfectly, and we build the Gaussian process and we sort of just assume that it's stochastic. Whether it's, well, we know it's not stochastic, we know it's deterministic. The implications of that are unknown. And this is that's a known problem with this process. But currently it's the best way we have of handling this kind of data. But I'm afraid it's just a modeling choice. Okay. Anyone else? Okay, getting in the end. An example. So I've written a very basic simulator. It's not actually a simulator, it's actually just like one line of code that just outputs a simple function. But it does have an input parameter of theta. And here I have run this simulation for different values of theta, or fixed t at 0.35, 0.4, etc. So there's 4 different values there. And I've managed to output that data at a range of different values of x. So that's, consider that our space that we're interested in. I've also put on there some observations. So we've made some observations from some true process. They're slightly noisy. And you can kind of see from this, you can get a visual guess that somewhere between the orange line and the green line, we've probably got a good fit somewhere. Oh, it does just fit. So there's the equation of the simulator. And actually, for illustrative purposes, that's also the equation for the true process. You wouldn't normally know the bottom one. The bottom one I'm giving you because it's useful for this example, but normally this would be wildly unknown. This is why we build the simulator. But I'm giving you this now so that at the end, I can show you a comparison to see how well this process works. The top line is normally our simulator. So that would normally be our weather model, our Navier-Stokes, whatever. And that would be hugely complicated. So what do? So we run the simulator for a range of values in t, in this case, all the t values between 0 and 1. We provide some priors on theta and the hyperparameters. What they are doesn't particularly matter in this case, just that they are provided. We run an MCMC algorithm, in this case for 100,000 steps. and we get some posterior samples, and we find that theta is equal to this. Great. So what does that mean? Well, remember, we know that theta also comes with a paired model discrepancy. So we'll check that model discrepancy in the end. But first, how well does this do? So we've built a Gaussian process that's supposed to approximate the simulation output. Looks like it's done all right. Pretty well. It's got the general trend, considering we didn't tell it that. I think that's not bad. I'm going to zoom in a little bit on 5 to 10. X equals 5 to 10. So all I've done there is just chop off the first half and just look at the second half. And you can see that actually it's not doing quite as well as we thought. So our uncertainty estimates miss quite a lot of the simulator output. Why this happens is partly due to data. It's also partly due to picking a bad prior. But to be fair, it's not done a horrendous job of picking out the general shape. Okay, so assume we've done an okay job here. Let's move on, see what the rest has done. I should now come with a warning. It's not a bad warning. Calibration procedures are very good at masking fundamental modeling problems. So in this case, you saw the equations before. So this is now showing you in blue, we've got the true process, which we wouldn't normally know, the observations, which we would know, and we can see that the observations are actually really quite close to the true process. So whoever made those observations did a fantastic job. They are somewhat different in shape, I would argue, from our simulator. So it's possible then that our simulator is perhaps not as well designed as we first thought it was. And actually, you could argue that there's some big differences in design, especially from reality, especially around here. You know, the simulator seems completely flat, but there's something else going on here that our simulator's just missing. Okay, so this is slightly concerning. Well, let's check the model discrepancy process. So in this case, we've perhaps not done as good as we thought. We've got the trend, I would argue. You know, the blue line here is the difference between the true process and what the simulator is saying. So the blue line is everything we haven't captured in our simulator. So this could be one particular process that's happening in one particular space. It could be a small interaction somewhere between two different things. It's not a big problem, but it's big enough that it's causing some big oscillations that we're missing. And our model discrepancy term is not capturing all of that nuance. I think it's doing quite a good job at capturing the trend, but that's not really good enough when we've got uncertainty bounds. So why is this happening? Obviously, I should say this plot, you can't normally construct this because you wouldn't normally have zeta, which is the atmosphere. So you can't normally look at this plot. But in this case, it helps to explain the narrative of what's going on. So yeah, it does an okay job for now, but it's not perfect. Okay, so we're coming towards the end now. So the MCMC steps are quite archaic, I think is not a bad way to put it. So, I mean, they obviously there's all the usual difficulties with fitting MCMC to this kind of stuff. You've got the high dimensionality problem. You're potentially dealing with a lot of parameter variables, hyperparameters and things. The matrix inversion is also expensive. There are some ways around it, but again, if you're dealing with massive amounts of data, it becomes very difficult. And the samples in this particular case were very highly correlated. That was because we're using a implementation that was in MATLAB that was written about 23 years ago, I think, that uses just a very simple metropolis within Gibbs. This whole process needs modernizing and speeding up and everything else, which is what I'm planning to do. So I'm currently working to improve the computational aspect of all of this process. And I'm using a Python package called JAX, which has been developed by some geniuses at Google. JAX lets you write just-in-time compilation code. So if you have some routines that you repeat frequently, you can compile them such that the code, I don't think it goes quite down to like machine level code, but it's so much quicker than just using your NumPy or your scikit-learn algorithms or whatever. It also includes baked-in automatic differentiation, support for CPUs, GPUs, and Google's TPUs, whatever they are. And as I say, it all comes wrapped up in this nice Pythonic NumPy and SciPy API. So it's really very impressive. It is still ongoing. We're expecting quite significant speed increases. I'm currently seeing about 10%, 10 times speed increase over the MATLAB code. And that's in quite a naive sense. I expect this to increase significantly further yet as well as we use more advanced techniques and things. It's a very naive sense of speed increase there. I'm also using a package called Michi, which is developed by Matt Graham. He is based at UCL Advanced Research Computing Center. This is a Python package that's used for simulating Hamiltonian dynamics on a manifold. Currently, I'm not actually doing any of that stuff, so my 10 times increase is just based on using something completely basic. I'm hoping that the performance increase will be retained as I start to use gradient-based methods and then get further efficiency in the better mixing from the sampling methods. Okay, I am there, I promise. Summary. The weather and climate models are complex and expensive. That's not news. GPs are flexible, they're non-parametric models, and they have relatively cheap uncertainty estimates once you've calculated your means. The model discrepancy in Bayesian calibration is essential. And I think that's the point that I really want to get across from this, is that you're not trying to just fit your model parameters with this, you're also fitting a model discrepancy term. So you fit your model parameters and you learn what's wrong with your simulator. And the computational acceleration is ongoing. And I have a bibliography that I'm not going to run through because I think I'm out of time. Thank you.
Thanks so much, James. That was fantastic. I don't see anyone charging in, so
That's good.
I think we have time for a few questions. Maybe I can start off with one. So you're looking at this massive speed up. So I was wondering, before the speed up, how was this doing some model selection, making model comparison, and does this change with the speed up and being able to fit many more models?
Well, so it would definitely help you fit more models. I suppose it's not a huge issue. So currently, I think the MCMC schemes were taking about an hour to run on this very simple problem. Quite how poorly that will scale up to a much bigger problem, we're yet to see, especially using these newer technologies. So there is perhaps an argument to say that the model selection case is perhaps difficult because you kind of want to use the best knowledge in the first place from your experts, and you don't necessarily want to tinker with that too much. Maybe if they've got 2 or 3 ideas about what might work, what they can try, maybe try a different covariance kernel or something like that, then perhaps that would make a difference. I don't see it being a huge issue until you get to the massive problems.
Any more questions? Yeah,
speeding up the computation will help with issues that you're having in the MCMC. Are you saying that you would use a more advanced MCMC method, but that takes too long to make?
Yes, so that's the original problem, I suppose. So the MCMC chains that are being produced are, because it's using such a basic method, they're all very highly correlated. So you're not actually getting a very good effective sample size out. the main problem with that is then, so you could increase the speed of evaluating the model, which is what the work in JAX is doing. And then you get further increases in speed by using something like Michi, which will then, you get more efficient, better samples per iteration. And the hope is that combined two will allow for this amount of data to be used to be increased.
Yeah, basically mentioned about the parameter to basically to overcome the identifiability issue, you say we have to implement like knowledge physicists and possibilities of what actually is going on in the atmosphere. So how do you exactly incorporate that knowledge into your GP5?
How? No, it's not obvious. So the original paper here includes some sort of regression terms, which I completely left out. And I left them out because there was already a lot of notation involved in this. So you can include regression terms within your mean for your Gaussian processes. Whether that is beneficial or not is very much up for debate within the Gaussian process community. Some people would much rather just let the hyperparameters and the covariance structure capture all of that variability, and you just condition on your observations. Some people actually like having the explainability of having some sort of regression functions involved. Which is easier, which is more restrictive, which is better? It all depends on your application and what it is you're trying to capture. It is a hard problem, and it is by no means obvious in how to do that.
I have a question on the model discrepancy for delta. I didn't quite understand how that's estimated alongside theta. Does it have its own like function form with its own factors? You mentioned that it was a non-parametric method, so is it that? And also, just connected to this point, when you showed the simulation, the simulated data, the example, you showed it for specific values of t.
Yeah.
So could you maybe merge my original question within the context of the example to explain it in a kind of practice?
I'll answer this one first. Okay, so your question was on the delta term here, on this model discrepancy. So we're assuming that it follows a Gaussian process or multivariate normal with zero mean. And from that, we're going to give it some sort of covariance structure, which is defined by this covariance kernel function at the bottom here. And for that, it will have its own set of hyperparameters.
Okay, so it's just that it's all multivariate normal.
Yeah. And what was the other bit? Sorry, that was.
So when you showed the example, you had different values of t. Yeah, this one. And I didn't quite understand in this case what the flow logic is. So you have the observations, and then you tested out different values of t, what the curve would look like to see which one is closest to the observations. And that's like to show us like which curve is closest to the observations, right?
Yeah, so
then
that's.
if this were real data, you would just have the points, and then you would run the estimation on it, right?
Yes. So in this particular case, it's very easy to plot, which helps. So whilst you can, if you were doing a much bigger model with multiple variables, you could still do this. You could still run your simulation for 4 different values, and you could still plot something somehow. All I'm doing here is doing it for illustrative purposes. I'm saying this is what the simulator output is for this particular value of t. So I suppose it is the same. When in an actual application, it would be a lot harder to produce a plot that looks like this, I suppose.
But would you normally do that in an actual application where you just have the points and you test it at different t values?
Probably not, because you'd usually be going to some practitioners who sort of know what theta is anyway. So I suppose in this particular example, I've gone in blindly saying I don't know what theta is, and hoping the algorithm will find it for me. Whereas in the real world, you sort of have a pretty good idea of what theta is. you know it's going to be within this kind of range, probably quite a small range actually. What you want to do really is, given that knowledge, pinpoint it, and then define your model discrepancy.
I think that might be our time. So let's thank James again. Two very brief announcements. The next talk is going to be given by Eon. It's going to be next Friday. And the second one is we still have a couple of slots left for next term. So I sent an email about this. So if anyone would like to speak, please tell me, or I will chase you. Physically as well, you know. Also, we might have the possibility to be able to invite people. So we've got a couple of external people who are going to, other PhD students who are going to be visiting next term. So if there's someone you know at another university, I think in the UK, apparently we can't pay for flights, but who knows? Then come and chat to me or Leandra as well, because we might be able to bring them along next time. Thank you.